API, Application Programming Interface, right? ABI is basically an app binary interface. So if you've got, let's say, a kernel, you might have an API that includes a read call, okay, with a certain parameters and a certain return value. But the ABI is how does that actually get passed in? Are we using 16-bit integers or 32-bit integers? Do the arguments get pushed left to right or right to left? Where does the return result get returned? Is it in a register or is it on the stack? So that's kind of what we're talking about in GCC calling conventions. How is it that we are going from one function to another and then coming back? And the things we need to know are, how do we get parameters passed? How do we get something returned? And how do we make sure that that any temporary values are saved? Okay? So if someone needs to use registers are saved. So that basically when you call a function and then come back from that function, if you had one of your local variables stored in a register, you don't want it to be blown away. So here's what our stack frame is going to look like. We'll have the arguments that the call are pushed onto the stack. Okay? We have, and as we're reading this, we need to realize that this is the top of the stack, right? Because it's ESP. So this is towards the bottom of the stack. So this is confusing, actually, that I'm presenting it this way, for two different reasons. It's confusing for reason number one, because the top is at the bottom, and the bottom's at the top. It's confusing for reason number two, because in x86, the stack, as you push, decrements the stack pointer, right? So it goes early and earlier in memory. So if we thought of memory 0 is up towards the top and memory FFF down here, then you'd expect the stack to be going this way. So just keep that in mind, okay? That this is the top of the stack. So the caller is going to push some arguments onto the stack, and then it's going to make what assembly language call? Fabio? Call, right. So it's going to do call. Call is going to push the EIP on the stack. Why don't we just push the EIP on the stack directly?
Because normal instructions can't read or write.
Yeah, you can't read or write the EIP directly. In fact, if you want to read the EIP, here's how you do it. Make a call to another subroutine, and in that subroutine, read the EIP on the stack and return it. So you could write such a thing. Okay, and then the function itself, so here is what the previous function kind of put on the stack, if we consider that the call pushed the EIP on the stack. And then below is what the new function, the currently executing function, is going to be putting on the stack. So it will do a saved EBP. Okay, that is, it will take the current EBP and push it on the stack, and then it will set the new value of EBP to the top of the stack as it exists, as it's just entering the function, right? So now you have EBP points to an old EBP, this EBP points to an old EBP, and so on. And then local variables, etc. Gary, what might etc. be? That is, what might it be storing on the stack besides local variables? Return addresses of what? Any function calls that it makes will, I guess theoretically they're going to be on the stack temporarily, and then they'll come back off. So yes, that's officially true. Katie. Anything else? Besides local variables. What else might we want to put on the stack? In fact, what might boot main have put on the stack in its first few instructions?
Scratch space.
So scratch base, actually that's, yeah. So we've got the local variables, And we've also got the registers that we want to save, right? And so that's, in fact, what boot main does. The first thing it does after pushing the EBP, setting EBP to ESP, it then goes ahead and pushes several registers that it's afraid are going to get, that it'll blow away, that it would then presumably restore at the end. So scratch spaces are even. If you want to access an argument, you get it via EBP, right? You know that EBP plus 1, well, let's just say plus 4, okay? So 4 bytes. EBP plus 4 is the return instruction, which you don't care about, right? But EBP plus 8 is the first argument, and EBP plus 12C is the second argument, and so on. So we can easily find those at positive offsets from the EBP.
Are argument 1 and argument 2 the arguments that get put onto the stack when the idiomatic registers are filled? For like because aren't there registers that take the first
No.
6 or something?
No, in x80, no. We're not using registers for doing parameter passing. We're just passing it on the stack. That it would be a valid interface to use. It just doesn't. You just don't. So, and then the local variables get accessed as negatives off of the EBP. All right, because they are farther towards the top of the stack. And the compiler knows where each variable is. Some variables, of course, are in registers and don't exist here, but others are here, and it knows what offset it is. So if you look at a negative 08 of EBP, that's going to be somewhere here, and that's going to be some variable. Questions on that?
So
Drove.
when you're decrementing the stack pointer from that EB down to that next space, so as we saw earlier, like, so is it only going to decrement when it starts for just the amount of local variables it has to start with? Then it can kind of play around, right? If it makes more calls and then push the stack pointer.
So your local variables are determined at the time you compile, right? We know how many local variables you have, so we can reserve this amount of space. As you're making calls, where that can be dynamic, right? Depending on a particular execution path you take through the code, you may make 1 call or 2 calls or 5 calls or 10 calls. And so yes, that will make the stack grow and shrink on every call. Okay? But it won't affect this. And kind of the steady state is here once you've returned. Does that make sense? Okay. So the stack is this contract between the caller and the callee. There's actually a little more of a contract too. But the first thing is, when we enter, that is when you first start the first line of code in a function, EIP points to the first instruction of the function, right? Because that's where you're executing. ESP plus 4 points at the first argument, right? That's going to ESP points at the return address, right? And then when we leave, just after the return, okay, so we're at the return of our function, the return assumes that the EIP you want to go to is on the stack, right? By the way, if you ever want to set the EIP to something you want, push a value on the stack and call return. That's basically what that does. So return will cause the instruction pointer to get popped from the stack. The stack pointer is now going to point at the arguments pushed by the caller. So basically, if we do a push 1, push 2, call foo, right? Then the stack is going to contain 1, 2. As we call foo, it's going to push the return address. And when we come back, the return address will be gone. So our stack pointer is going to be pointing here after the called foo, right? So basically, just like it was before you called foo, right? So the call instruction is going to be is not going to modify the stack.
Can we turn off the
Sounds good to me. You want to figure out how?
The slider.
Or I could send it from 1 to 3 and see if that quiets it. Thank you. So does that make sense for the stack? So who's responsible for popping the arguments?
The caller.
The caller. Because here they are on the top of the stack. Could you set up a situation where the callee is responsible for popping arguments?
Yes, that's just not what whoever designed it did.
Yeah, and in C doesn't work that well, right? If you have a program that doesn't have variable length arguments, so we know for every procedure exactly how many arguments there are, then you might as well have the caller pop those arguments. It can work. Right? So that way, if you have 10 calls to a function, you don't have to 10 places have to then go and pop those values off. But in C, since we have variable numbers of arguments, who best knows how many arguments were pushed? The caller. So the caller pops. Go ahead.
Doesn't the callee need to also somehow be able to know that so it can use all of the arguments?
Well, by convention, you probably want to have some specification of how many arguments there are. Okay? You can imagine an ABI that actually pushes a value, which is how many arguments are there, but we don't do that. And so I think we talked about the fact for printf, it uses a format string to determine how many there are. But nothing prevents you from calling printf with more arguments than that. They just won't be looked at. And other calls, I think we saw one, the execv, where you need to put a 0 at the end. So it can run through its list of arguments and find the 0. Okay. And since we put a 0 at the end, or let's even look at printf, where we've got the format string. We want the printf to be able to find that format string. So in order to find the format string, it has to access that from the EBP at a known location. So it has to be the first argument. Okay? You couldn't have the format string as the last argument because it wouldn't know where to find it. It wouldn't know how far up to go. And so that's why for C normally, the arguments are pushed right to left so that the first argument is right there and easily accessible. Does that make sense? Okay. Now there's another contract, or part of the contract. One contract has to do with the stack. I suppose another contract with the stack is don't blow away stuff that was below your call function. You're not allowed to just go in and change stuff, right? That would be like buffer overflow attacks, right? To try and make a function misbehave. The return result. Oh, and the called functions, though, are allowed to trash the arguments. That kind of makes sense, right? If you have a C program with parameters, you're allowed to modify those parameters. I don't know, like let's say you have a count, and you say while count minus minus is greater than 0. Okay? It's going to actually be changing that on the stack, but that's okay. So you can't rely on these having maintained their original value. The return address is in EAX. Sorry, the return value is in EAX. And then EAX, EDX, and ECX may be trashed, even if it's a void. Right? So even if it doesn't return anything, AX, DX, and CX, from before the call to after the call, may be different values. So if you've got something here in EAX that you think is important, it's your responsibility to save it. Where are you going to save it?
Maybe in a different register than save, or maybe on the stack.
Possibly a different register, possibly on the stack, right? Stack is probably a good place. So these are caller saved registers, the ones that are not guaranteed to be maintained. The callee saved registers are the ones that are guaranteed. It's the other registers. And so therefore, the callee has to push those and save them and restore them before it returns. Okay, does that make sense? Questions? Yeah.
It seems like this makes very extensive use of the stack. I thought writing to memory was slow.
Well, yeah, but we don't have a lot of registers. So it's not like we're on a RISC machine with, many tens of registers. So we don't have anything besides memory.
Okay.
Okay, so let's look at the prologue. So the prologue is the code that gets emitted at the beginning of a function. We push the EBP as I described, and then set the stack pointer to point at that EBP. And then, what the heck are we doing here? So this is main. Main is going to return f of 8 plus 1. So we got to call f of 8. Push an 8, call f. Where's our return result? Where's f of 8? EAX, because that's what we defined as our contract, that the return result would be EAX. So add 1 to EAX, and then undo what we did before, right? So move
So set the stack pointer. I think that moves the base pointer into the stack pointer, so now the stack pointer is back where.
Oh, yeah. Yeah, this restores, this basically blows away all the local variables you may have initialized, or you may have allocated. Pop off the EBP, and then return. And then we have the same sort of prologue for other functions as well. So in F, we push the EBP, move the ESP into the BP, and so that will give us this chain that looks like, and I'm going to go from bottom to top. So we're going to have the old EBP, and then we're going to have 8. And then we're going to call into F, and so we're going to have a return address in main. And then in F, we're going to push an EBP, which points to here, right? And then we we push 8 of ESP. So let's figure out what the heck is going in there. So this is ESP, right? And so ESP positive accesses from the stack pointer here are going to be parameters. So this is going to be, this is ESP 0, 4, 8. So that's the value 8. So it's going to push 8 again, right? Because that's the G of X here, right? And then we call G. So we're going to have a return address in F. G is going to again push an EBP. Our stack pointer is now going to point to here. We're going to save EBX because we're going to be modifying it. So saved EBX. And then we have to calculate x plus 3. So 8 of EBP.
So that's 8.
EBP is pointing to here. Okay. And so EBP plus 0, EBP plus 4, EBP plus 8 is our parameter, which is 8. We move it into EBX. We add 3 to it. And then we move that into EX. Now, why didn't we just work in EAX? Right? Why didn't we just move 8 of EBP into EAX and then add 3 to EX and not worry about EBX?
So we could demonstrate saving registers?
Yeah, there's no good reason. It's not as smart as it could be. Because we had to save EBX and then restore EBX. But does this make sense? So when we're done with this, we've got 11 in EAX. And then we start undoing everything.
So I noticed at the start of main, we push EBP. What is EBP before we start main?
In general, for when we start main, I don't know. In our case, when we're looking at the kernel, we will set EBP to 0 to signify it's the end of the world.
So that's like something that the kernel takes care of before it jumps into main in the
Exactly.
Cool.
Yeah. Because yeah, it's got to set initial values of all registers when you're starting a program. And so EBP, it would make a lot of sense to be 0, and ESP should be pointing at some nice stack. There's another question here?
Yeah, can you explain like why EBP gets updated the way that it does?
So the reason it gets updated the main reason it gets updated is for debugging. Okay? The main reason we have these threaded stack frames is it so we can look back on the stack and see what was running. All right? We could write this all without using stack frames. Okay? Just working off of the stack and using the stack pointer. That would all work. But you wouldn't be able to do a backtrace in GDB, and that wouldn't be very fun.
So what exactly then is a stack frame?
A stack frame is contains the stack local variables for this call. And let's see how we're defining it right here. The way we're defining it right here is it doesn't include the return address. So it includes stack frames for this call, saved registers, any param, for functions that it calls, and the return address for functions it calls. So if we go up here and look, what we've got is a previous function called, right, the callee pushed the arguments and then made a call. And we're going to call this part of their stack frame. And now our stack frame is where we save our EBP and then save any local variables. If we want to make a call, we do pushes, and so on. So each one of these contains all the local variables. And if we look in the previous stack frame, we can find the arguments. Okay? And by just chaining these back, we can figure out where we came from. And if we look at the saved instruction pointer, that'll tell us where the code is. And if we have a symbol table, we can then go find out what function it was and what line number it is and so on. Does that help?
Yeah, and so when you were drawing in like a few slides from now, were you drawing in the other direction?
Yeah, so yes, I was drawing it the other direction. It's just to keep you on your toes. G could be as simple as this, right? G just could be, don't even bother with the stack frame. Right? Just do this. And for leaf functions, you don't need a stack frame even for going back. Okay.
Could F just be jump G?
What's that here?
Could F just be optimized as jump to G? And
Oh,
G
sure.
scale that?
Yeah, I mean, yeah. All right, just this is probably a refresher, but when we compile a C file, it actually generates assembly language, right? So that's the compiler. Actually, before compiling, there's another phase, which is pre-processing, right? So there's a preprocessor that actually runs first, and then we have the compiler. It generates assembly code. There's nothing that requires this. This just happens to be how the GCC system works. And then we have an assembler, GAS, that creates a .o file, right? You don't normally see the ASM file. It's temporary that then gets removed. See, I take it back. It's probably not a temporary that gets removed. It's probably piped from here to here, such that we don't need to write it out on a disk for the reasons we talked about on Wednesday. Multiple .o files, object files, get linked together into what by default is a.out. So when you say gcc foo.c, it produces an a.out. This is actually a linker. LD sure looks like it's load, but this is really
So what's the D stand for?
a link. What stands for load? But I'm telling you, it's a linker. Okay? So a linker takes together multiple .o files and says, this .o file called foo, and this .o file defines foo. I need to actually update this call instruction to refer to where foo actually is ending up. Okay? So it resolves all these references. It's the ones that'll say undefined reference foo, right? If you never actually define foo anywhere. And then the loader runs in the kernel. So this is part of the kernel that actually takes an executable file and throws it into memory. Okay? Questions on this? Yeah.
So, like when you compile, you get from the .c files to the a.out, and then when you actually go to run it, then it takes.
Yeah, it's when you actually run ./a.out, that will run the loader and put it in memory. Because certainly it doesn't go to memory to actually try and execute it.
What does the loader actually do?
You're going to have to see some of what the loader does. So part of what the loader does is you've got your executable file that's got different parts to it. Some of it's code, and it just copies those into memory. It's got data that is all of the initialized variables, the globals. It needs to actually, it's got that data there, and it needs to write code to actually copy that into the global space. There's a BSS segment, which is all of the global variables that are initialized to 0. That's so common, especially in C, because that's a default, that instead of having a bunch of zeros in your executable, it just has a thing that says, make a space this big of zeros. Okay? So you're going to have to be doing some of this stuff in your operating system. Other questions? Okay. Emulation, just to give you a very brief overview, right? We've got a PC running Linux. This is for Knuth. There's a PC emulator on it. What are we using? QEMU. Yep. And on top of that, we got JOS or XV6 or something else. So it's just a normal program running under Linux. No special privileges. How does it emulate? Well, I'm going to back a second and say this is how it could emulate, and there's a lot of work that that has gone to try and make it faster. But this is one way you can write an emulator, is just define some variables. You're going to write it in C, define some variables that'll hold the registers, define a big-ass array to hold your memory. And then your emulation goes like read an instruction, decode it, figure out what it is, do the operation. If it's register-based, read from the registers and put it in the registers. Kind of just do its thing. And then update the EIP. Okay, so you're playing computer. If you want to access memory, well, you might have read byte, write word, write word, and so on. And read word is going to kind of figure out where are we in memory. Right, where is this address? Is it in the BIOS? Is it in extended memory? Is it in low memory? Maybe we have different arrays for those. And the same thing for writing. Okay? So the hard part of emulators is both being faithful and being fast. And then for hard disk, it just uses the file system, right? So it actually, normally for the hard disk is going to create one big file on the file system and then treat that as the hard drive. And then similarly, it kind of uses the host for lots of other things, for the clock, for the keyboard, all that sort of stuff. Okay. Questions? All right, let's go over to Lecture 3, which is mostly about GDB. But first, some trivia, or administrative trivia. So we have a Gruder. Mars, here is our Gruder. We're currently planning on 7 to 9 in Beckman 105. All right. For how many people does that time not work? 6, 7. 7 people, 8. All right. Were you also available not before that, but after that?
Yeah, I am pretty flexible.
Would 8 to 10, so let's say I made it 8 to 10. Would that work with you, Mars?
Yeah, I could even do 7 to
That's like a bone. Yeah. How can one go wrong with that? So does adding that extra hour from 9 to 10, of those people who said there were a problem, raise your hand if that helps. Okay, so you tell me now, 7 to 10 or 8 to 10? 7 to 10? Okay, so I will update. It's on the syllabus right now as 7 to 9. I will update it 7 to 10. All right. And we picked Wednesday because stuff's due Thursday. And someone asked, like, when on Thursday is it due? Because the lab didn't say. Well, it says now, 11:59 p.m. on Thursday. So the last second of Thursday. I've gotten almost all of your lab GitHubs, you know, where you've asked me to participate in that, and that's great. Except I realize as I'm going to be going grading that some of them are like, you know, Caterpillar at GitHub, and like I don't exactly know who Caterpillar is. So if your GitHub name is like not your name, put an author.txt file in your repository. Put your name in there and make sure that is part of the repository, okay? So that I can give you credit for your Caterpillar. Okay. Lecture recordings are linked from the schedule. So if we look at the schedule, so we've got, there was a video on the first lecture, but it really did not turn out well. And the second lecture, I made a video, but I didn't actually put a link to it. So I'll show you what a video might look like. So it's basically the screenshot. And normally it would have sound, but the sound was broken. Grade scope. I actually started grading these earlier this morning, and what I found was about a third of you, when you submitted, didn't actually associate the pages with the questions. And you could submit without that, but it makes my life a lot harder. So let me show you what you need to do. So when you do a submittal, it's going to show you your PDF and the pages in your PDF. And what you need to do then is say, okay, hey, you know what? That page belongs to this question. I know there's only one question. But when it comes up to me for grading, it says it displays me nothing. And I have to go find the pages and do this stuff. So
There's also an assign pages sequential button. Probably does this every time.
let's see what that does. I don't know. No. It said this page will be deleted. Not has been deleted, but will be deleted and undo. It's a little confusing. I don't care. You can go look and see whether assign pages works. I will let you know next time if again, it's not assigned. But, okay, it's just a simple thing. Grading. So grading the labs. So we're looking at basically the automated test is one part of it. Okay. The automated test that you get to run, and I'll go ahead and run as well just to verify. The automated test, you can see the test. So feel free to look at that if you want and see to figure out what's going wrong. It's in a file called something like grade.lab1, something like that. And it's Python code, I think. Yeah. Okay. Anyway. Also, I'll be looking at your code. So I'll be looking at your code for like errors. Like maybe you did pass the test, but there's things that are wrong. Okay? And I will be looking at it for style. The style I want. Okay? So there's simple things like style, like are you using spaces or tabs? What should you use? No, you shouldn't use spaces. No, you shouldn't use tabs. You should use what the code that's already there does. Okay? In general, whenever you're editing code, make it fit the style that's there. Okay? So JOS, I think, uses tabs, and I think XV6 uses spaces maybe. So if you're doing JOS, you use tabs. If you do XV6, do spaces. So match the surrounding style. it's always so frustrating when you're doing introductory programming, like to say, you know what, the indentation isn't random, you know? It actually needs to be indented correctly. So, but not that I think this will be a problem here. Okay, so errors in style and then the automated test. That's basically it. So, questions on that? All right, GDB. So let's talk about homework 1 first. So from homework 1, we had this in our assembly language for the boot. We had some code that did some stuff, and then we did move L start ESP. So start was a label at the very beginning of the code in boot.asm.s. So like the very first thing was dot start. The dots are assembler directives, and actually, was it a dot start or a start colon? Was it dot start? Fine. All right. So then what we did is moved the location of start into the stack pointer. Okay. Where did our code, our boot code, get loaded into memory? Where did our boot code get loaded into memory? That is, where did you set your breakpoint to begin with to first start debugging the boot? 7C00. Yep. So here was our code. And start refers to this, right? Yeah.
In GDB, is there any way to access these symbols? Or do you just have to look at the assembly dump and like check what the memory address is and then use that?
You can. GDB has symbol files. We'll talk about that a little bit later. By default, we're setting it up to use the symbol file of the kernel because most all of your work in JOS and XV6 will be in the kernel, and so therefore that's the one you want the symbol table for. You could use other symbol tables, and for the boot, I looked and I didn't see a symbol table for the boot code because at one point I tried to go do that, so I don't think there's a symbol table for that. But in principle, one could.
You'd have to reconfigure the build system to make that,
and then you could load it into GDB, and then you'd be able to do stuff like look at start or set a breakpoint on boot main. So here's our code. The stack pointer is set to here, and then we call boot main. So if the stack pointer is set to here, right, and we call boot main, what happens to the stack? Ashley.
I guess, well, that's the start of the stack, and so it'll start overriding whatever's there before.
You would think, except the stack.
Oh, it goes the other way. Yeah, yeah.
So these are purple. Yeah, this what they weren't stupid when they set this up. So therefore, we're going to have now the return address in start. I guess it would be the best description of it, right? That's the label that contains the code is start. And then the stack pointer, of course, is going to be decremented by 4. All right. And then there's other stuff that happens here, right? And then eventually we find the entry point. So we have a pointer to the entry point, and we call it. And so that is going to then cause us to have the return address in boot main. And our stack pointer will now point to here. So when we start the kernel, that's what it's going to look like. Yeah.
Can you explain the syntax around for entry?
Yeah. Okay. Entry is a int32.
Yeah, but the void.
Yeah, no, I know this is the hard part. Yeah. So here's what it is. So the star heap, so what we've got is this looks like a function, right? It's missing the function name right here. There's a star instead. So if we just made this a function name, this would be like a void. It returns a void, and it takes a void. So it doesn't take any parameters, returns nothing, but it's a pointer to a function. And when you call it theoretically, you should really be calling it as star entry, like that. And in fact, you can call it that way, but you can also just call it the other way as well, because like what else would you be doing, putting the parens around? Okay, but this really is more meaningful, is more correct to what we're thinking of, because entry is not a function, it's a pointer to a function. Does that help? Okay. All right.
Why is it relevant to do this as opposed to just calling elf pointer entry?
Elf pointer entry is a integer,
Which is the address.
which is the address of the function. So we need to cast it to a function. And so this is what it looked like. So when we get into boot main, it saves a bunch of stuff, right? We've got now on the stack the old return address. And then, just like we saw before, we're going to have the old EBP. We'll set up our SP to point there. And then we push 1, 2, 3. Now, this may be slightly different depending on whether you use Knuth and when you used Knuth as far as when I set. So I think everyone probably has these three, but what this number is going to be different because it depends on the compiler settings that were used. Okay? But basically this is save registers, right? These are the ones that aren't allowed to be stomped on, and presumably they're used in here because if the compiler didn't use them in here, there would be no reason to save them. And then reserve space for local variables. So we have some saved registers here. And we have local variables here. And I think actually what you guys have is 0x1c. Does that sound familiar? Okay. So, questions? All right. So the stack, when we get here, looks like this. If we did x/24x $ESP, it looks like this. All this stuff from 7C00 on is not part of the stack, right? The bottom of the stack is 7C00. And the bottom of the stack you don't get to write to, right? Because it starts out empty, pointing there, and you go up above it. So what is this stuff? Sarah. So from 7C00 on is what? It's the code. This is the first instruction of our boot block, right? Because remember, that's where it's got to load. We set our stack pointer to point right to the beginning of our code. And then we got 7C4D. Okay, so 7C4D. Wow, that's really confusing because these numbers don't match. So we'll fix that. I don't know.
C4D.
7C4D is what I have. Okay, now.
It's in the opposite.
Yeah, so these are going high, lower, 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 lower. This is just to make sure you have to look at this and figure out what's going on in each particular case. Okay. It's really because this is the order in which stuff was pushed on the stack. This is the bottom of the stack. This is the top of the stack. This is where we return from calling boot main, right back into start. Is it ever going to return? Yeah, hopefully not. Saved EBP. Notice the EBP is 0. Saved EDI, saved ESI, saved EBX, and then we've got 1C worth of local variables. Here, I got the 1C right. Okay, so this is when we subtract 1C from ESP. That's this here. 1C, let's just make sure. 1C is going to be 7 4-byte values. 1, 2, 3, 4, 5, 6, 7. That looks good. Okay. It's a little confusing because if you actually look at the number of local variables there are fewer than 7. So it's quite a little bit a question to me of how exactly all these 1C are used. I'd have to disassemble the code and then look at how each one is used. And then, eventually, we call entry. and that then pushes the return address. So this is the entry return, which is back into boot main, which also shouldn't return, although there is code to deal with returning, right? I think if it does return, doesn't it do some sort of a box triple fault or something to try and get the debugger's attention? Does this part make sense? David? Yeah, I got it.
Why is EBP 0?
EBP is 0 because just when we first start, we set stuff to 0. I don't think the processor guarantees what it will be. I think we explicitly set it to 0. Did you guys notice that it initializes a bunch of registers to 0? The very beginning, it sets one register to 0 by doing a exclusive OR of the register on itself. Okay? Because, of course, the exclusive OR of two things that are the same is going to be 0. So that'll 0 it out. Why not just move 0 into there? I guess it's slightly better.
As opposed to 2 bytes of
Yeah,
instruction,
so we
say XOR and then which register.
Okay, so we save 3 bytes of instruction. Yeah, that's great. I asked you to note which of these non-zero, what are the non-zero ones? And so we've noted everything except this one. And this one, let me tell you how I did it. I went in GDB and I started going through, actually what I did is I calculated EBP and noticed that this was going to be EBP 4, 8, 12, 16, 1, 0, 1, 4, 1, 8, 1, C, 2, 0. So it looks like 2, 0 of EBP is whatever's writing in here. And then you can go look in the code and see what writes into 2, 0 of EBP. And it turns out it's this line that says EPH equals PH plus some offset.
Wait, what do you mean into 2, 0?
So this local variable
Yeah.
is hex 2, 0 away from our EBP.
Yeah, okay.
So that's how we get there. Okay.
And this is like the 5th local variable. Is that why you knew that it was far down the stack?
I didn't know it was the 5th local variable. I actually just looked at the code that actually assigned to 2, 0 of EBX and looked at the corresponding source and saw that it was assignment to EPH. Okay. Commonly in functions, it's pretty straightforward of, you have some variables and it's exactly those variables that get saved and you know the order. I'm not sure exactly what's going on here.
So when I did the memory dump, that memory address had a 0 in it. Do you know what's up with that?
Could have been saved in a register instead. Did you use Knuth?
I did not.
Oh, okay. So, yeah, I had started this not using Knuth either. So we have different build tools and different version, different settings for the compiler. No wonder. Other questions? All right. And here was the code. And I lied. It wasn't 2, 0 of EBP. I calculated wrong. It's 1C. So this was the code that moved something into 1C of EBP. That's the associated source code, right? This is just pulled from block.asm. Is that what it was? Yeah. And so we saw him assigning to EPH. So that must be what that is. For GDB, you got to use i386elf GDB. Just like you got to use the i386elf whole suite of build tools and so on. All right. Here's what happens. When you run make QEMU, I don't know what's so hard about that. QEMU GDB or QEMU Nox GDB, make creates a .gdb init file. So normally when GDB runs, you give it an executable, and it's going to run that executable. In our case, we have an existing running executable, which is QEMU. So the make will actually create a GDB init file that contains enough information for GDB to find it. So you got to run the right GDB from the same directory because we want it to read this init file that just got written in a separate window because you want it to both be running. And this is kind of what's in there in the GDB init. It target remote localhost 28178. That's the important thing that says this is where you're going to find that process you're trying to debug. And this says use the kernel symbol file. Okay? So JOS also does the same thing when you make the QEMU GDB. Yeah. Yeah, I'll talk about that in just a second. These GDB init files can run lots of stuff on your behalf. And so in order to provide some safety, GDB in recent versions has tests that you have to actually explicitly turn on to allow this local.gdb init to run. So I built and installed a new version of GDB this morning that is more current, okay, and that fixes some problems we had with your GDB. But it has a security test. So therefore, you need to follow the Piazza post to create a GDB init in your home directory that says allow this sort of shit. Right? Please do read these GDB init files. Right? So it's in the Piazza post. But until you do that, GDB will all of a sudden no longer be working correctly to connect to QEMU.
Give you directions for how to do it, though.
Yeah, it does give you directions, that's right. It does tell you exactly what to fix, and I just put that in the Piazza post. For JOS, by the way, if you want, you can just make GDB. It's a few less characters to type, and it'll actually run GDB for you. Help, this is the meta information, help or help a command or help on various topics. You can abbreviate commands, so continue is fairly long, CONT is shorter, C is even shorter. And in fact, even shorter than that, let's say you're single stepping with step, S, return, S, return. What if I had 0 keystrokes, right? Just hit return and it'll do the last thing. Some special abbreviations, SI and NI, step instruction, next instruction. And for stepping. So stepping, a single source line is step. Right? We're going to be doing a combination of assembly and source level debugging. Certainly at the beginning, as we were looking at booting, it's assembly level debugging. Feel free to use source level debugging, right? To the extent you can. If you have to drop in an assembly, do that. But step I steps a single x86 instruction, and next I is just like step I, except it is supposed to skip over call instructions. As you may have found when you were debugging the booting, it did not skip over instructions. Okay? And I have yet to figure out exactly why that is, but I'll tell you, once you get into the kernel, step I starts working again.
Does it maybe have something to do with the lack of a symbol file? If the symbol file
Step I shouldn't care, because step I basically says, is the current instruction not a call? Step. If it is a call, set a breakpoint right after that. That's what it should do.
You mean next I should do that?
You're right. Next I is the one that should, yes, look and see that it's a call. It may have to do with the mode running. I'm just not sure why that is. Continue, we've already seen, right? So the way you start running is you hit continue, because basically when you run QEMU GDB, it's going to stop right at the beginning. Okay? And then you continue from there. Finish, I find very useful. If I accidentally step into a function that I don't want to be in, I call finish, and that will run to the end and go back. Advance was my workaround that I used for the fact that next I didn't work. So advance, and you give it some location, either a symbol or an address, will run until the instruction pointer reaches that. So it's kind of like doing a break, and then a continue, and then deleting that breakpoint. So it's like a one-shot breakpoint. So what I would do is go to the call, and then just basically advance to the instruction after the call. Because I really got tired of walking into read seg.
Is there a way to restart without having to quit GDB and then quitting GDB?
No. Yeah. For the recording, the answer is no. Yeah. But I make it pretty quick. I quit GDB. I do my kill all by using bang kill, which will rerun my kill command. I switch windows over to the other. It's already quit QEMU. I do bang. I just hit up arrow and return to execute the next thing. And then I go back and hit up arrow I. There, bang I.
Is
Yeah.
bang kill control AX?
So yeah, it's like control. So there's kill all, QEMU dash, is it system i386 or something? It's something like that. Okay, you have to get the name of the process right, but then it'll kill it. Control AX works pretty well, because, right? So you can do that from the QEMU interface, except I run screen, which uses Control A to mean something else, and so it doesn't work. So that's why I don't use that. You can set breakpoints. As we see, the asterisk allows you to just put in address value. More commonly, you're breaking at a particular function name or possibly line number or something like that. You can modify those breakpoints. Conditional breakpoints can be really handy. So if something happens the 5th time you're calling it, or only when there's some certain value, like some certain parameter, then you can add an if to your break. So break, some location, if, and then some condition. Watch points are really handy. So this is, someone is trashing this address. I wonder who. And so you can watch an address or a variable and just see when it gets written to. And it'll break when it gets written to.
Can you do like watch for a register?
You can't, I don't think you can watch registers. I don't think. You can also watch, so this is the expression, you can watch an address as well. And there's rwatch, actually, that'll stop when an expression is, when something is read, not just written. It's interesting. We've seen x/x. x/d and x/i print the data in different ways. So in decimal, which is rarely useful. In instructions, so this is basically disassembling. You can also use disassemble. So this would be, right. You can print expressions. So for instance, you remember that the ELF, we read basically our executable file into 10000. So our header then we looked at to see if it looked like a valid header and used it to read the rest. This is one way we can print it, right? Basically take the raw address, cast it appropriately, dereference it so it doesn't just print it out as a pointer. And we get to see all of the fields of the structure. Or we can do it the low-level way. x/10x to say 10 values in hexadecimal at that location, and here they are. You get to decide which you like better. But in general, if you can print. You can look at registers with info registers. Look at the frame with info frame. So you can see where the arguments are, where the locals are. You can see the previous, all that stuff. Backtrace I find very useful. So how does backtrace work? Nandika.
It does a thing with the back pointers.
Yeah, follows those base pointers or frame pointers. Okay. And this seems like a little bit of a lie, not enough registers in memory. I think it just got to the end. Layout ASM is very handy. So layout ASM, let me look at an example. By the way, notice as I type SSH in that it never asks me for my password. You should immediately adjust things so that it never asks for your password either, using SSH keygen. Okay? So just look that up. How do I log in without putting my password every time? Okay, just use this. So you want to do that. Any particular time, it takes more time than just typing your password. But you'll quickly recuperate that time. Okay. All right, so oh, right, I was trying to So there's my GDB init. And now it's not complaining anymore. And what did I want to do? Oh, I want to do layout ASM. So layout ASM, well, let's see, break at OX7C00, is that right? Okay. So our first instruction is a clear interrupt. And so I get a window that's showing my assembler. And if I then single step, away I go. This is the part that was failing in the GDB that was installed on Knuth up until this morning. It would show the window, but it wouldn't allow you to actually single step, which means that's not a very useful window. In fact, it's less than useless, useful. So, and you can also do layout, is it reg? Yeah, so you can see your registers as well. So I find this much more useful to have the context to see what I'm doing as I'm moving. Okay. Sorry you didn't have it before now. You can, yeah.
Oh, I was just going to comment. There's probably a better way to do this, but for the restarting GDB, I just said while true, make QEMU done in my shell. And then in the other window, just while true, make GDB, and semicolon pkill QEMU and done. And so I just quit GDB and it kills QEMU and restarts it.
It's kind of insane, but I love it. So yeah, I'm gonna definitely start doing that. So, and you can of course just make a shell script that does those two that you put in a bin directory that you can just run each time. Right. So I like that a lot. You can change the values of variables. The var word here is not strictly necessary. However, they're set to set other things as well. And so if your variable name happens to conflict with one of those, you're trying to set something you didn't realize. You're not setting your variable. So just always use set var and then your variable name. The symbol file. So the symbol file determines variable names, function names, where the source code is for those functions. So as you see in the GDB init, for xv6, it sets the symbol file to kernel. Right? xv6 is very simple. There's no subdirectories. It's just all a flat directory. So the kernel symbol file is right there. For JOS, they actually use subdirectories. And so this is the location. So in lab 1, break boot main doesn't work because boot main is not part of the kernel. Right? It's part of the boot process, which is a separate executable. And in JOS, if you've got a user program you want to debug, as opposed to the kernel itself, you've got to specify another symbol file. So you've got to specify obj, user, and whatever the prog name is. Okay, and we will be writing user-level programs. So you'll need to know that.
Is the obj directory dynamically created every time you do a compile?
So there's no obj directory in Git. So the obj directory is created by doing a make.
Right.
When you do a make clean, one hopes everything in there is gone. Yeah, but it isn't all dynamically created. Whatever is updated by make. Learn GDB well. So time spent perfecting your use of GDB will be repaid not just in this class and not just, well, most of you are seniors, so you don't necessarily have future classes, but I bet you're going to be using GDB in the future. Okay? So learn it enough, look at the manual, spend some time doing that. When I was first working using Unix, we talked about the man pages, and there were these different sections, section 1, section 2, section 3, and they were, of course, in those days, all were available bound. And then there were a bunch of manuals that were available, like for the C shell and for VI and for other things. And so what I would do sort of during my lunch hour is I just sort of started at the beginning of that, multiple thousands of pages, and just would kind of go through and read. Say, okay, there's a command called cut or something, and here's kind of what it does. But what was useful is, in the future, think, I need to do such and such. Oh, wait, I remember seeing there was a way to do that. Because if you don't even know stuff is available, right? Maybe there are GDB commands you don't even know. So that's why it'd be worth reading through the manual. Okay? And Bash, or whatever your shell of choice is, and Vim or Emacs, depending on which side of the Holy Wars you're on. Again, you want to perfect your use of those because you're going to be living with them all the time. So the example you gave of the while, true, do, run my GDB, kill all, done, is a great example of some just little shell scripting that will make your life lots and lots easier. Because you don't want to do things, you want to write programs to do things. Okay? Or perhaps write programs that do things. For Vim, if you are not kind of expert at Vim, run Vim Tutor and go through it. Okay? And my suggestion to you is force yourself to use commands that you know exist. I'll give you an example. If I am, I can't think about it very much. My fingers know Vim. I don't know it in my brain that well. So let's say I'm here and I want to delete to the F. Okay? So some people might go X, 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 X. No. Right? Delete to the F. Well, how do you find the F? FF deletes to the F. Okay? Because F in some character goes to that character. The problem is I didn't want to delete the F. I want to delete up to but not including the F. So D, T, F deletes up to but not including. So T goes forward. No. But this is going to repay so much time because you're going to be using this over and over and over and over and over again. Okay? There are similar things you'll need to learn for Emacs. All right. A good cheat sheet, by the way, for GDB is at this location, and I provided you that cheat sheet on the next couple pages. So, is there anything more I want to impart? Yes, a couple things. So today, Mars is having Gruder hours. Today, 7 to 10?
Yeah.
Oh, boy, it's great, 7 to 10. So Mars, Gruder, 7 to 10. I am going to have office hours from 2:30 to 3:30 in B105. This is standard. But I may be there a couple hours more. I'm not sure, depends when my wife gets done. 3:30 to 5:30, maybe. All right? So feel free to come by, and I'll be happy to help you out with things. I know the lab and the tracing the EBPs and all that stuff can be difficult. I'm happy to do that, help you with that. The repositories are going to be cloned tomorrow. Basically, I'm going to sync them at midnight tomorrow night. And so if you have to be late, because I remember I told you there were late hours, let me know when you're late. Like say, oh, I just, I submitted a new version for lab 2 5 hours late. Let me know so I can go copy it, because I'll just have the older version. Your homeworks should be back this afternoon, and then the labs sometime over the weekend. Questions? Lab 2 is out now, although I suggest you not start it until you finish lab 1. And it's due, let's just check when it's due. I think it's in 2 weeks. Two weeks. Yep. Okay. All right. See you guys on Wednesday.